Last week, we've seen the big idea of learning in a neural network, the idea of loss functions and backpropagation to get our gradient vector to minimize the loss function, moving in the direction of steepest descent. This week, we'll look into gradient descent, how we actually tune all the parameters of a network using backpropagation. Let's take a look in the 2D case for some simple analogy first, and I promise that the idea itself is really simple. Say we are given a 2D function, but we don't know what it looks like, and right now we are at a specific point on this function. Now the question is, how would you minimize the output value of the function with only local information? Since we can't see the entire function, the best approach is to calculate the derivative at our current point. The derivative gives us the slope of the function at that point. Let's take a look at a full picture of a random function for some understanding first. If the slope is positive, it means the function is increasing as we move to the right. To minimize the function, we should move left instead, as the value will decrease in that direction. Conversely, if the slope is negative, the function is decreasing as we move right, so we should head right to keep reducing the function's value. The size of this left/right nudge is proportional to the value of the slope. So let's start moving, shall we? Since right now our slope at the point is positive, we move left once. At our new point, the slope is also positive, but now it's a lot smaller, so we move left again, but at a much smaller step. And again, and again. Now let me reveal the full function to you. It's just simply x squared. There's no actual explicit rule as to when to stop this repeat of steps, so we usually say, hey, stop this after doing it 5 times, or something like that. But we can see right now we've reached a point where the slope is close to 0, indicating that it's getting close to a local minimum, so let's stop there. So what do we do there? 1. We got a point on the function. 2. By calculating the gradient at the point, we know if it's increasing or decreasing. 3. We then minus the value of the gradient and get a new input value. 4. Now calculate the new point on the function. 5. We repeat. This is basically the gradient descent algorithm, and it's the exact same thing in neural networks. We have our set of parameters in the network, whether they're weights, biases, or other variables, which we collectively call theta. Then, by subtracting the gradient vector, nabla c, from each one of our variables respectively, which we calculate at the current point on our loss function, we get a new set of parameters. It's important to know that each variable isn't subtracting the entirety of nabla c. Rather, it subtracts its own corresponding partial derivative from nabla c. This means each parameter is adjusted individually based on the slope of the loss function with respect to that specific variable. Really, a great analogy to think about for gradient descent is literally a ball rolling down a hill, mathematically. Okay, but there's still something missing to the story, learning rates. Imagine we have this loss function and we're starting at some initial point. As we run the gradient descent algorithm for a few iterations, we might find ourselves stuck at a certain point. While this point might look like a minimum, it's just a local minimum, not the global minimum. To the left, there's a deeper pit with significantly lower loss that we just cannot reach. Here's the problem. Since we're close to this local minimum, where the gradient is close to 0, gradient descent takes very tiny steps. Our progress slows down dramatically and we basically get stuck. Wouldn't it be nice if we could give this ball a little boost? Something to propel it out of the local minimum and help it move towards that global pit? That's where learning rates come in. The learning rate is an arbitrary constant that we multiply with a gradient vector to control the size of our steps. By scaling the gradient vector with this constant, we can adjust how big or small our steps are. If the learning rate is too big, our steps are so large that we end up bouncing around the cost function everywhere without ever settling at a minimum. If the learning rate is too tiny, our steps are so small that it takes forever to reach a minimum. And it's called a hyperparameter because of that, as there is no real systematic solution as to, wait, so how large should I set this value? You just run the gradient descent algorithm and see how fast/slow our loss updates are, and then just adjust accordingly. Now let's talk about the gradient vector in detail. This isn't just the gradient for a single sample. It's actually the average gradient vector across all the samples in our dataset. Why do we do this? If we only calculated the gradient vector for one specific example and adjusted our parameters accordingly, we'd get better at predicting just that one example. Another example might want the parameters to shift in a completely different direction, and so on. If we go in a specific direction for a specific example, we don't get better on all the samples overall and have an overall smaller loss. By taking the average gradient across all the samples, we are effectively finding the overall direction that minimizes the loss for the entire dataset. This way, we're not just improving for one or two examples, we're improving for all of them for our model. So you might start to wrap your head around just how computationally expensive this entire algorithm sounds. Calculating the gradient vector for one sample is already a hefty number of work with countless partial derivatives multiplying each other. Then doing this for the entire dataset, and then doing that again every time we take a step in gradient descent? That's crazy computationally expensive. How to optimize the training process of a neural network is a very huge part of the research as well, because if you can develop algorithms that could allow the network to train to optimal performances in a shorter period of time on less computational power, you save millions and billions of dollars on electricity and the environment by saving greenhouse gas emissions, and just allow AI researchers to do their work faster. One popular variation of gradient descent is stochastic gradient descent, where instead of taking the average gradient vector of all samples in our dataset as a gradient vector to using gradient descent, we only take a small portion of the samples in the dataset to take their average gradient vector, and move on to another small portion of sample in the dataset in the next iteration of the algorithm. The size of this portion is usually what we call a batch size, as each batch represents a small portion of the samples in the dataset that do not repeat for taking the gradient vector at each iteration. Well, that is until we reach the end of the dataset. We just go back to the beginning. It just saves time, a lot of time. There are countless other variations of gradient descent that try to optimize its performance, and you can do the research yourself as to what those methods are and how they improve from gradient descent. So, congrats! This is all to the basics of neural networks, and it's all old stuff in the 1980s. And you can see why this wasn't something mainstream for researchers at the time, as there is simply insufficient computational power to make the best use of these algorithms. At the end of the day, neural networks at their core are just function approximators. Think of them like the Taylor series or Fourier series, mathematical tools that approximate functions by summing simpler components. In the case of neural networks, we have a model that takes inputs, say 5 inputs, and produces an output, say 1 output. In reality, there may lie some fundamental connections between our inputs and outputs, like some underlying formula that we cannot see and know. Take, for instance, the ever-changing prices of stock markets, influenced by countless factors like economic indicators, investor sentiment, and global events. Or consider the preferences of people's taste in music, which may depend on complex interactions of cultural trends, personal experiences, and psychological patterns. Those systems are examples of complex, high-dimensional problems that we cannot directly well model with mathematics. The magic of neural networks lies in their ability to approximate these complex, high-dimensional functions just through learning patterns in the data. And as we learned throughout these videos, all that they're doing is adjusting the parameters to minimize the error, gradually converging to a function that maps the inputs to the outputs as closely as possible. I don't know. It ain't magic no more to you, it's all just math exercises. And researchers are still walking on this passive study to dive deeper into exploring different practices of how to achieve AI, or make these existing methods better. Next, we'll start talking about the basic ideas of natural language processing, the relevant neural network architectures to deal with language, and eventually what makes up ChatGPT. I promise you, I won't get into the mathematical notation of those things any further, as I am not confident for myself that I am teaching the correct thing.